Today we will be continuing our discussion of street routing problems with an introduction to the principles of graph theory. Now, graph theory deals with graphs that look like these examples that we have on the board, for instance. Basically, all a graph is a set of vertices or points on the graph. So in this case, if we look at this graph over here on the left, that would be A, B, C, D, E, and F are our vertices. And these vertices are connected by edges. So all of these little lines that we see connecting all of these different points, these would be our edges. So when we have a graph like this, we have our vertex set, which is basically just a list of all the different vertices in the graph. And then we have our edge list. Now, the edge list lists all of the edges in the graph, but it takes into account a couple of things that we can see when we have these kinds of graphs, and those are loops and multiple edges. A loop is basically just an edge that connects a vertex to itself. So in this case over here at A, we have this loop right here. Basically, it pretty much just looks like a circle that starts and ends at point A and doesn't touch any other vertices. This would be a loop. It's connecting A to A. The other thing that can happen is what we call multiple edges. Multiple edges is basically where we have more than one edge connecting the same pair of points. So in this case, from B to C, we have 3 edges, and from D to E, we have 2 edges. So when we are making our edge list, loops we list as AA, for instance, if it connects A to A. Normal edges, so say this one going from A to C, we would just call this edge AC. If we have multiple edges, such as BC, shows up 3 times, so we're going to list it 3 times in our edge list. All right, so another concept that kind of goes along with this is the concept of the degree of a vertex. And all that is basically is just how many edges are touching that vertex. So when we are determining the degree of a vertex, all we have to do is just look at the vertex and see how many lines are coming out of it, basically. So a loop counts as 2 in this case when we're figuring out the degree. Regular edges count once. So if we look at this graph, the degree of A in this case would be 3. For B, it would be 1, 2, 3, 4. C, 1, 2, 3, 4, 5. D, 1, 2, 3. E, 1, 2, 3, 4, 5. And F, 1, 2. Now we can classify the edges in a graph, or the vertices in a graph, based on whether their degrees are even or odd numbers. So when we refer to odd vertices, that just means vertices that have odd degrees. Whenever we refer to even vertices, that just means vertices that have even number degrees. So in this case, the odd vertices in this graph would be A, C, D, and E, and our even vertices would be B and F. All right. Now, one other concept related to graphs is the concept of connected versus disconnected graphs. In a connected graph, like this one, all of the vertices are linked together as part of one continuous piece. A disconnected graph would look like this example that we have over here, where we have vertices B, C, D, and E that are all part of one continuous piece, and then vertex A is over by itself. It's not connected in any way to the rest of the graph. So this graph is in 2 separate pieces. We would call this a disconnected graph. Another thing that we see in this graph is what we call a clique, and this is basically where we have a set of vertices where every vertex is connected to every other vertex in that set. So B, C, D, and E form a clique because B is connected to all 3, C, D, and E. C is connected to all 3, B, E, and D, and so forth and so on. The other concept that you can sort of observe with these two graphs is what we call simple graphs. So a simple graph is basically just a graph that does not have any loops or multiple edges. So this graph would be an example of a simple graph. All of the edges are single edges, and there's no loops. This graph over here, we have loops and multiple edges, therefore this is not a simple graph. One scenario where simple graphs come into play is with sort of our classic example, what we call friendship graphs. So I've drawn an example over here, kind of in the middle, of what a friendship graph might look like. Basically, this is just a graph that shows connections between people. So the vertices in this case are different people. I've just called them A through H letters just for the sake of simplicity. And these edges, the lines connecting them, represent the relationships between all of these different people. So this would be, once again, an example of a simple graph because there are no loops or multiple edges in a friendship graph like this. The last concept that we'll talk about with graphs is what we call paths and circuits. A path basically is just a set of consecutive edges that you're following. So, for instance, if we look at this graph up here at the top, if we went from B to D to C, we follow two edges, B to D and D to C, so that would be a path, and we would say because we follow two edges that the length of that path is 2. A circuit is basically just a path that starts and ends at the same vertex. So if we went from B to D to E and then back to B, we followed 3 edges, BD, DE, and EB, and so we would say that this is a circuit of length 3. Now, there's a couple special kinds of paths and circuits that we refer to as Euler paths and circuits. When we are dealing with paths or circuits, we can only use each edge that's involved once. We can't recross an edge. If we do that, then it's no longer a legal path or circuit. So all an Euler path or circuit is a path or circuit that uses every single edge in a graph exactly once. So here's an example of an Euler path down here on the left side. So we have 4 vertices, A, B, C, and D. We've got 4 edges connecting those 4 vertices. And we're going to start at A, we go to B, C, D, and then back to B. We've used every single edge in the graph exactly once. And because we start and end at different vertices, we start at A, end at B, we would call this an Euler path. An Euler circuit is different from an Euler path in that rather than starting and ending at different vertices like an Euler path, we are starting and ending at the same vertex. So here in the bottom right corner, we have an example of an Euler circuit. So we have 6 edges connecting 5 vertices, A, B, C, D, and E. So if we go A, B, C, D, E, C, back to A, we've covered every edge in the graph exactly once, and we've started and ended both at vertex A. Therefore, this is an Euler circuit. Now, in the next couple videos, we will look at how do we find Euler paths and circuits for graphs, as well as how can we use these, and sort of their applications. Thank you for watching, and as always, I'm happy to help with any questions you may have.